Good afternoon, and welcome to hand-wavy chemistry, where we do not delight in the details, but rather bask in the big picture. Except for today, where we will permit ourselves a moment of unnecessary detail to answer the question, why do metals conduct electricity? Before I get into the detailed explanation, I first want to give you the standard hand-wavy explanation that involves a sea of valence electrons. Here we have the more traditional hand-wavy explanation for why metals conduct electricity. We think of the metals as being atoms suspended within a sea of valence electrons. In the model you see in front of us, the marbles represent the metals and their non-valence electrons, and the water represents valence electrons. The metals are not particularly attached to their specific electrons, and so instead are happy to share them equally throughout. The electrons are still confined within the body of the metal because of the positive charge in the nucleus, which attracts them, although they're not really concerned about which electron belongs to which atom. So, if we were to apply a potential and begin to add more electrons in, we see that the electrons flow out the other side. This model works very well for explaining why electrons flow through metals. It also explains very well why metals are malleable and can be reshaped. Because the bonds between all of these metals are very fluid, they're not rigid, if you are to strike and move the metal, it doesn't really make a difference. Because all of the metals are still sharing all of the electrons amongst them all, and they are all still satisfied that the charges are balanced. In a similar way, metals are ductile and can be drawn out into a wire. The sea of valence electrons once again has no problem with this, as the shape of the metal does not affect the way that those atoms and their electrons are interacting. We can also easily think about heat being transferred through the metals. As they are able to share energy and electrons, they should be able to share heat, no problem. Compare this idea of metal atoms sitting in a sea of valence electrons, not really concerned about how those electrons are distributed, to something like this. It is a small section of the structure for diamond. All of these carbon atoms are held rigidly in place. These bonds are defined, they cannot deform. And if we strike diamond, it will not bend. Instead, it would have to break. Due to the rigidity of its bonds, it is not malleable. Because all the bonds are fixed, it does not conduct electricity, although it is a very good conductor of heat, because heat could be transferred as vibrations through those bonds. However, there is an issue with this model. Since the valence electrons hold all of these atoms together, you would expect that an increased number of valence electrons would make a stronger metal, one which has a higher melting point. That does not agree with the trends that we see. For this, we need a more detailed explanation. In order to understand what happens when metals come together, we first need to understand how bonds form. When two atomic orbitals come together and overlap, they can do so in a positive manner or a negative manner. Let's start by thinking about an s orbital. It's a nice spherical shape. In this case, they are both in the same phase. We've colored both of those s orbitals black. And as they come together, we see the overlap occurring and a positive interaction. This is a bonding orbital. It is lower in energy than the orbitals before they came together. Now in this example, the s orbitals are out of phase, so we have colored one black and one white. As they come together, they have a negative interaction, and they form an anti-bonding orbital. This anti-bonding orbital is higher in energy than the original atomic orbitals were. Every time we manage to get orbitals to overlap, there will be a positive interaction and a negative interaction. The positive interaction can give rise to a bonding orbital of lower energy, and the negative interaction an anti-bonding of a higher energy level. And we don't just have to stop here. We could take this bonding orbital and have it interact with another one. So let's think about lithium. Lithium has a single electron in its 1s orbital. So we could bring the two together and we would get a bonding and an anti-bonding orbital. And we would have two electrons in the bonding orbital because that is stable. Now if we take our two lithium atoms and get another two lithium atoms and we bring those together, well, all of our orbitals will interact again. Those two bonding orbitals that each contain some electrons, well, they can interact. There'll be a positive interaction and a negative interaction. And those empty anti-bonding orbitals will also interact, having a positive and a negative interaction. Now we could take this molecule of 4 lithium atoms and get another molecule of 4 lithium atoms and bring them together. Now we have a molecule of 8, and a lot more energy levels have started to occur. We could take this molecule of 8 and bring it into contact with another molecule of 8, and a lot more energy levels occur. If we keep doing this, we end up with energy bands. A bonding band and a non-bonding band. An electron that were to be placed into that non-bonding band will be able to skim along all of these different atoms. It would not be held in place in any way at all. It would be free to move and conduct electricity. And this overlapping and bonding of orbitals isn't just restricted to s orbitals. It occurs with p orbitals and d orbitals and even hybrid orbitals. And as we add in more and more different orbitals and have more and more of them get involved, we just get different band structures. But we always end up with this continuum where we have a filled area at the bottom and an unfilled area at top, which is able to conduct electrons. In fact, if we didn't incorporate other orbitals like p and d, we wouldn't be able to explain the conductivity of a lot of metals. Think about alkali earth metals. They have 2 electrons in their valence shell. Their s orbital is full. If all we did was bring 2 s orbitals together, we would get a bonding and an anti-bonding orbital. And we'd have 4 electrons. 2 would go into the bonding, 2 would go into the anti-bonding, and overall there would be a bond order of 0. There would be no reason for these 2 atoms to bond. But when we can incorporate p and d orbitals, now we get more states, more places that we can put bonding electrons and generate a reason for the metal to stay together. This idea of having different bands is also very important in the world of photovoltaics, where we will use light to put electrons up into a conducting band. But that is a story for another time. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in the future, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.